Alright, so I'm going to try to swing through this flowchart really quickly. So this is composed of individuals belonging to the same species. Kind of right away, I know it is a population. Example of that, just a group of humans, a group of squirrels, group of dolphins, group of ants, group of birds, group of trees. Over here, number 3 incorporates all of the population. So again, different populations, different organisms, different species together. We call that a community. So humans with plants and ants and, just multiple species together in one area. All right, moving over to number 5. So this one is population ecology. It's talking about, okay, well, what does increase or decrease the size of populations? Over here, number 6, this is asking about the number of individuals per unit area or per volume. We didn't do the aquatic stuff, but it works the same way. This one is population density. So how many are there in a given area? Usually kilometers squared. All right, moving over here, what is the equation for population density? That one is the population size divided by the area, typically given in kilometers squared. Moving over to number 9, a description of how individuals are distributed. This is clumped, uniform, random, and again, just make sure you're able to pair it up to each of these, which I'm not going to go through. One of the things to pay attention to is that these two do not impact one or the other. But for example, you could have 5 individuals in a kilometer squared with random assortment. You could have 5 individuals in a kilometer squared that are clumped. You could have 5 individuals that are this or that. It doesn't matter because the population density is still going to be 5. So this is just how it's arranged. This is how many there are. And I know people think like, oh, clump means there's a lot more. It doesn't mean that. It just means that that's how they're distributed inside of that given area. This tells you how many there are, and this is just how they're arranged. All right, number 13. So gives a description of how particular ages fit into different categories. That's age structure. Don't get it mixed up with sex ratio. So there are different ranges. I've given you one. You need to make sure you know the others. But anything between 14 and 44 is called pre-reproductive. Obviously, anything higher than 44 is post. Anything under 14 is pre. Number 15, just make sure you're able to identify the following graphs as expanding, decreasing. This one says contracting, and this one says stationary. Another word is stable. All right, moving on. Over to number 16, which I gotta find over here. Number 16, a resource that a population can't live without. So that means that they need that is a limiting resource. An example of number 16, space, food, water. All right, moving on to number 18. An individual's probability of survival, and that depends on the size of the population, blah, 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 blah. That's just density dependent. Okay, this one is density independent. Again, has nothing to do with the size of the population. So what are some examples of this? So like this one says the same effect. It means that it doesn't matter what the size of the population is. Over here, number 19, what is density dependent? Again, food, water, space. Over here, density independent items are tornadoes, hurricanes, things like that. All right, population growth that is slowed as it increases in size, blah, 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 blah. This is carrying capacity. So while I'm saying blah, 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 make sure you understand, like you compare up that definition here. All right, moving on to number 23. So the number of offspring that an individual can have at a given time. You can call this population growth. Over here, this is to calculate population growth rate. And actually, now that I'm looking at it, I should have probably had a better definition here. But the equation that you're going to use for number 23, because I gave you two. I gave you one that included birth rate and death rate, but I said we're going to use it later on. I gave you the simplified version where it's final population minus initial population divided by time, and then you divide it by initial population again. This is important. When I ask you for the percent, you have to convert the decimal, because it is going to give you a decimal, into a percent form by multiplying by 100. You got to be careful up here, because this one, for predicting population size into the future, is a exponential population growth model, or you can just call it growth model. What's the equation for that one? Well, that's nt equals n0 to the natural log of rt. Now, when I ask about r for this one, it has to be in a decimal. So again, it must be in a decimal for this one. Make sure you understand like how these play together, because one of the big problems is going to come from here, making sure, do you understand the variables? Do you understand what to do with them? All right, moving on to number 24, if I can find it somewhere around here. Well, I'll just branch off. Oh, here we go, number 29. So under ideal conditions, basically unlimited food, water, you're going to have exponential growth. This is going to create a J-shaped curve. R tends to be very high in this case because, again, you're growing exponentially, meaning R, your reproductive rate or your reproductive percent, is really high because you're growing very quickly. Now, this is different than number 31 because initially it was exponential, but it has begun to slow down because the population is approaching that carrying capacity. This is going to produce an S shape, and this is leading to R being lower or almost zero if you basically flattened out. So, but again, make sure you understand how these two tie together. How do those two tie together? What happens when the population becomes larger than the carrying capacity? We call that overshoot. And then eventually it's going to come crashing down because there's not enough resources. We call that die-off. All right, moving on to number 37-ish somewhere. So this right here is talking about K and R strategists. I'm going to let you guys figure that out. Make sure you know some examples of K and R strategists. Down over here are survivorship curves. Again, there's 3 survivorship curves, type 1, type 2, type 3. Again, just make sure you know which one goes with which and some examples of each of these. Now, I know I messed up here on 46, so I would skip this one on your study guide. It doesn't really matter if you don't. I would focus on this one. So the relationship between 2 species that live in close association with one another. This one I was looking for symbiosis, but even mutualism would probably work there. Number 47, this kind of ties into this one. 2 species that are competing for the same resources cannot coexist. That's competitive exclusion principle. Finally, the interaction types. These are pretty simple, pretty straightforward, just plus or minuses, and make sure you give it a name. And then finally, a species that plays an important role in its community. That one is a keystone species.